Okay, so first, anybody have any homework questions? Anything like that? Okay. Well, we're talking about vectors. We're on our way to talking about 2D kinematics. Oh, let's talk about the exam for a second. So in the next 2 weeks, we have forget that. Okay, bear with me. Almost there. All right. So next Wednesday, we have exam 1. And the topics for that are going to be everything up through vectors. So there's not going to be any 2D kinematics on it, which is sort of the next thing we're going to get into. But there will be vector stuff. The way to get ready for the exam is to go back over practice problems, the daily problems, make sure you understand how to do all those. The problems that I give are going to be similar to that. They're going to take the same sort of approach and thought process as those. Then the week after that, so what's that going to be? Wednesday, that'll be September 20th. And then 22, 25. 9:25 to 9:29 is going to be lab exam 1. And the topics for that are going to be everything up through next week's lab. Okay, so be ready for those 2 things. They're coming up, the first exam and the first lab exam. And then right now you're working on a weekly assignment. And is that due tomorrow? Is that right? Yeah. So remember to do that. Okay, so we're talking about 2D kinematics of particles. And first we had to define vectors, and now we're going on to using vectors to define, so we need to define the position vector, the velocity vector, and the acceleration vector now that we've moved from 1D to 2D. So I'm going to start with the position vector. If you remember, it's probably a little hazy, but when we started talking about 1D kinematics, I said that there are two things you need to choose before you can assign a number to the position. Do you remember what those two things were? Not the two time ones that we also need for the constant acceleration equations, but what? Direction and position equals 0. Yep. So in 1D, before we could quantify the position, we had to choose the 0 position and the positive direction. Well, in 2D, you have to do the 2D equivalent of that. So similarly, in 2D, you have to choose. Can anyone guess what the two-dimensional equivalent of the 0 position would be? So the first thing you have to choose is a location in the real world where you're going to put the origin of the coordinate system. So of the coordinate system origin. And second, the 2D equivalent of the positive direction is choosing the orientation of the coordinate system, which way the x-axis goes and which way the y-axis goes. Once you have those, so once you've chosen those, the position vector is the vector from the coordinate system origin to the object. Okay, so if this is your coordinate system, and this is your object, the position vector is this. An easier way to think of this, so remember this, it's always, I think, a better way to sort of keep it in your head, is that the position vector, the components of the position vector are just the coordinates of the object in your coordinate system. Bless you. So, for example, if you have this coordinate system, and we'll go 1, 2, 3, 1, 2, 3, 4. And here's your x, and here's your y. And the object is here. what are the coordinates or what are the components of the position vector? And the way to think about that is just, well, what are the coordinates? The position vector is just the coordinates, so it's going to be +4 in the x direction. These are -3 in the y direction. Okay? The units for position, well, what you're going to see is that in 2D, the units are all exactly the same as they were in 1D. So for position, the units are units of length. And that means that the SI units are meters. Okay, any questions about position? Just think of it as the coordinates of the object at any instant. So now we have to talk about velocity vector. Velocity is a measure of how quickly the position vector is changing. And you can think of the velocity vector, well, every vector has two properties, magnitude and a direction. So a velocity vector is, okay, so the magnitude of the velocity vector is the speed, just like in 1D, the absolute value of the velocity is the speed. And the direction is the direction the object is moving at that instant. The units are length per time. And that means that the SI units are meters per second. And there are a few things that I need to say about the velocity vector. So notice there are 1, 2, 3 things. The first one is often in problems, you'll need to calculate the velocity, a velocity, from a speed and an angle. And you'll do it just the same way that you did the vector problems. So let me show you an example, like let's say that a problem says at the start of the motion, the object is traveling 10 meters per second. at an angle 30 degrees above the horizontal. Okay, so it'll say something like that in the problem. And what you have to do then is recognize that, okay, here's the horizontal line. This vector is at an angle 30 degrees above that, so 30 degrees. And it has a magnitude of 10, okay? And now, whatever coordinate system you're using, put this vector, the tail of this vector at the origin of your coordinate system. And calculate the components. So this velocity vector is 10 times the cosine of 30 degrees, 10 times the sine of 30 degrees. And so you get a vector of 8.665, and the units are meters per second. Okay, so very often in problems, you're going to have to calculate at least one velocity like that. The second thing to keep in mind is if an object is dropped, I don't know why I put that in quotes. I think I meant to underline it. So if an object is dropped at the instant of release, the object's velocity vector is the velocity vector of what it's dropped from. Okay, so an example of this is, let's say that a ball is dropped from a car that's moving 20 meters per second horizontally. Well, what this tells you is, the velocity of the car is horizontal at 20 meters per second. So can anyone tell me what the components of this vector are that's just pointing horizontally to the right? I guess it depends on the coordinate system, but let's use our usual one. Yes. So that's 20, 0. And now that you know that, that means that, so at the instant of release, the velocity of the ball is also 20, 0. It's not, going to stay 20, 0 because things are going to affect it, air resistance might affect it. We don't use that in calculations in this class. Gravity is going to affect its fall, but it's going to start at this velocity. Okay? And then the last thing that you need to keep in mind is, okay, so remember in 1D, when an object reaches the highest point in its flight, the velocity was equal to 0. Okay, remember that? So in 2D, you might think when an object reaches its highest point, the velocity vector is 0. But that's not quite what it is. So in 2D, at the highest point, only the vertical component of the velocity is 0. Okay, so what that means is if you choose your y-axis to be up when you choose your coordinate system, Vy then is equal to 0 at the highest point. That's what I'm always going to choose for a coordinate system in 2D free fall problems. So okay, this probably seems a little abstract, but let me sort of explain to you what's going on with this. So we're talking about like an object that's in projectile motion. Okay, so its 2D path would be like that, okay? And we're saying that when it gets to the highest point in its flight, you can't say that the velocity vector is 0. All you can say is that the y component of the velocity is 0, okay? So to make sense out of that, imagine this baseball player. He doesn't have very good throwing form, but okay, so he threw this ball as far as he could. Okay. And somehow you knew ahead of time that the highest point was going to be right here, and you set up a ladder because you're sure that the velocity is going to be 0 when the ball reaches the highest point, okay? And you stand on this ladder confidently. There's you. You have a giant head. Okay? And you put your head right in the path, I guess the base of your skull right at the path of this ball when it's where it's going to be at the highest point, you know? If the velocity is equal to 0 when the ball gets to your head, that means that at the instant it gets to your head, it's at rest. And it just slowly nuzzles up next to your head, and that's it, okay? It sounds like soothing, therapeutic, you know? But, I mean, imagine doing this, like standing at second base in the Metrodome and having someone from the outfield throw a ball as hard as they can. You know intuitively that that ball is not going to nuzzle gently against your head. It's going to send you to the hospital or whatever, you know? The reason for that, so the way it works is when this ball gets thrown, it has a high horizontal velocity component of, let's say, 95 miles an hour. And it has a much smaller vertical component, let's say 5 miles an hour, okay? When the ball gets to the back of your head, the y component has gone from 5 miles per hour to 0 miles per hour. So that's part part's good. It has slowed down a little bit, but the horizontal component of that velocity is still 95 miles an hour. And, you don't want to have your head in front of that, So that's the way it works. That was sort of wordy, but the answer is only the y component of the velocity is 0 at the highest point. But just like in 1D, you're going to always use that fact if a problem mentions the highest point of a flight. Like right as soon as you hear that, tell yourself like, okay, I'm going to use the fact that Vy is equal to 0 at that instant. Any questions about the velocity vector? So the direction of the velocity vector is the direction that the object is moving at that instant. The magnitude is the speed. And then remember these three things. They're going to come in handy over and over again. And now we have to talk about the acceleration vector. Velocity measures how quickly the position vector is changing. The acceleration measures how quickly the velocity vector is changing. So acceleration measures how quickly the velocity vector is changing. In 1D, anytime you have acceleration, it means the object is changing speed. So acceleration means either speeding up or slowing down, and that's all it can mean. In 2D, there's a whole new thing that acceleration can represent. So first, it can, of course, mean that the speed is changing. You still can have speed changes in 2D. So speeding up or slowing down. But there's a new thing. So it also, and or, it can also mean that the object is turning. We haven't seen that before. In 1D, there's no such thing as turning. You're just moving along a line, going back and forth. But now we can have the direction changing. And so in 1D, any kind of, if you have acceleration, the object is changing speed. In 2D, though, you actually can have an object that's staying the same speed, and it's still accelerating because the direction of the velocity is changing. It's turning. Okay? An example of this is in old-timey astronaut movies, space movies. They always used to show the astronauts on this training device that gets you ready for dealing with really high G-forces. You know what I'm talking about? Okay, so how does this thing produce really high G-forces? Well, it starts out at rest and it speeds up till it gets up to speed. But once it gets up to speed, it's a constant speed as it's going around. So is there any acceleration? There's a lot of acceleration because at every instant, the direction of the velocity is changing, okay? And so the fact that this person is turning this whole time means that there's a big acceleration, even though the speed is constant. So the speed is constant. The big acceleration here comes entirely from turning. The units of acceleration are length over time squared. And the SI units are meters per second squared. And there's only one thing you need to keep in mind about acceleration. So notice in free fall and projectile motion, the acceleration vector is down with a magnitude of 9.81 meters per second squared. Okay, so what that means to us, since we're pretty much always going to put our y-axis pointing up. So if your y-axis is up, then the acceleration vector is 0 for x, negative 9.81 meters per second squared for y. Okay? Any questions about that? All right, so now we have the definitions of the position vector, velocity vector, and acceleration vector. So now we have to start to talk about how to use these in constant acceleration equations for 2D. And a lot of this stuff is going to be very similar to 1D. But okay, so here are the constant acceleration equations in 2D. So we'll say P sub I and V sub I are the position and the velocity at time equals 0. And P sub F and V sub F are the position and velocity at time final. Okay, so that's just the same as it meant in 1D. So the equations now, notice I'm going to start by writing the 1D equations, and then I'm just going to modify them a little bit to deal with the fact that we're using vector components in these equations now. So the first equation was VF is equal to VI plus ATF. And I'm going to duplicate these. We'll see that we'll use each of these equations twice. Okay. The second one, PF is equal to PI plus VITF plus 1/2 ATF squared. And I'll duplicate that one. And then the third one says 2A times the quantity PF minus PI is equal to VF squared minus VI squared. Okay, so far, this is exactly what we had in 1D. But now for everything that's a vector, we have to include components. So the reason that these equations are doubled like this is we're going to have one of these that has all the x components and one that has all the y components, okay, for each of them. So it's 6 total equations. So of these variables, we have p's, v's, a, and then we have tf, okay? Which of those are vectors? Is tf a vector? No, that's still, time didn't change at all going from 1D to 2D. But position, velocity, and acceleration are all vectors. So for the things that are vectors, we'll refer to the x components in one of these equations. So VFX is equal to VIX plus AX times time final. And then in the other equation, the y components. And same with this one. X is in the first one. Y is in the second one. And the third one, X is in the first one. Y is in the second one. So you don't have to remember any equations for the tests or anything. I'll give you every equation you need. But, you know, considering that you probably have these equations pretty well committed to memory because you're just using them a lot, remember that you can come up with the 6 equations for 2D by just putting the components in there like that. Okay, so now I'm going to list a set of general steps for 2D problems. It's very similar to the steps for 1D problems. And then we'll just start doing example problems, and we'll do a few of them, probably going on next class too. Okay, so here are the general steps for using constant acceleration equations in 2 dimensions. What was the first step that I listed for 1D kinematics problems? Yeah, right. Choosing, you have to choose those 4 things, right? You have to choose a 0 position, a positive direction. Those are arbitrary. And then you have to choose a time equals 0 and a time final. Those you have to get right, or you usually can't do the problem. Well, we're going to do the same thing in 2D. So first, choose an origin location for the coordinate system, and a coordinate system orientation. You can choose these however you want, but for these free fall problems, we're always just going to put the y-axis up. And now you have to choose the 2 instants. So a time equals 0 instant when you turn on the stopwatch, and a time final instant where you click the stopwatch off to look at the time. So I just want you to make a mental note of how that's the exact same thing that you do at the start of 1D problems. It's just the 2D version of it. Okay, what's the second step in 1D kinematics problems? Yes, list what you know and what you're trying to calculate. And you're going to do the same thing here. Now there's a lot more variables to keep track of. So the list of all the variables now is TF, A, but now A is a vector, so there are two components for that, okay? Same with all the rest of them that are going to follow. So we have A, we have the initial position, but that has an X and a Y component. Final position, initial velocity, and final velocity. In 1D, this was 6 variables because each of these things was defined by a single number. Now each one of these things is defined by 2 numbers, and so this is a total of 11 variables. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so now you're going to list out what you know and what you want. The third step that you're hoping is the last step, most of the time it's the last step, sometimes not though. You want to find one of the 6 equations. So of the 6 constant acceleration equations, and you want this equation to have, so that has the variable you're trying to find. And every other variable in the equation is known. Okay, so that's basically exactly the same as 1D. You just have 6 equations you have to consider now. And then last, if you remember in 1D, I said sometimes there's no equation that works. In that case, you want to solve for either A or TF. In 2D free-fall problems, you basically always just want to solve for TF if no equation works. So if no equation works, find something that lets you solve for time final, solve for TF, and then go back to step 2. Try again, basically. What was I going to say? Oh, okay. A couple things. I'll bring this stuff up again, but notice a couple things about these equations. The equations that have TF in them, notice that TF is the only variable here that appears in x and y equations, okay? Like notice if you look at the x's and the y's here, x's stay to the x equations, y stay to the y equations. The only thing that crosses over between them is time final, okay? That's what makes it useful to find time final, because a lot of times you can use like a y equation to find time final and then plug what you found into the x equation. And then also, 6 is a lot of equations to go through to see if an equation will work to solve for what you want. But notice that right away, you can most likely eliminate 3 of these equations in most cases. Because if you're looking for an x component of a variable, you can right away rule out all of the y equations, okay? So, all right, let's do an example. Finally. So we're going to get to, now we're doing a 2D physics problem. So let's say that there's this baseball player. You have to draw this picture. That's supposed to be his glove. No time to correct it. Okay, and he's going to throw this ball this way. So let's say that this ball is released with a speed of 40 meters per second, 25 degrees above the horizontal. So let's figure out first, how high is the ball at its highest point? And second, how far does the ball travel horizontally before it hits the ground? Okay, well, we'll start with part A. We're just going to figure out how high the ball is at the highest point. The first thing we have to do is choose our coordinate system, our origin location, our time equals 0, and our time final. I'm going to put I always just put the origin on the ground underneath where the object is at the start of the motion. So I'm going to put my x-axis there, my y-axis there. And what do you want to choose as time equals 0? Yeah, the instant it's thrown. Because we have information there. Oh, I have to give you a height too. So it's released from a height of 1.5 meters. Time equals 0 is the instant it's thrown. And what about time final? For part B, it'll be when it hits the ground, but for part A, it'll be when it reaches the highest point. Well, now that we've done that, we can think about what variables we know and what variable we're trying to find. Do we know how long it takes to get to the highest point? No. The acceleration we do know is 0, negative 9.81. Do we know the position at time equals 0? Remember, the position vector is just the coordinates of the object. So in this coordinate system, at the instant it's released, the coordinates are 0 for x, 1.5 for y. Anybody have any questions about that? This is the coordinate system, and this is the location. So all you're doing is coming up with the coordinates of that point. Okay, so pi is 0, 1.5. Do we know anything about p final? No, that's what we want. We don't care, though, about the x component. That would tell you how far horizontally it travels. The only thing we care about is how high it is, so that's pfy. So the variable we're looking for is pfy. Do we know the velocity at time equals 0? Yeah, we don't really yet, but we can get it from what we're given. So we know that this takes off with a speed of 40 meters per second. And it has an angle of 25 degrees above the horizontal. So in this coordinate system, I'll draw it over here. So here's our coordinate system. This is the vector with a length of 40 and an angle of 25 degrees. And so the initial velocity is 40 times the cosine of 25, 40 times the sine of 25, and this gives you 36.25, 16.90. And then do we know anything about V final? There's one thing we know, and it's the one thing that you want to make a mental note of as soon as you see that word highest point or high point. Okay? The y component of the velocity is 0. So VFY is equal to 0. We don't know anything about VFX. Funny thing is, it actually turns out VFX stays at 36.25, and that happens in all of our problems. But pretend like you don't know that, or it'll make you think that some equations are going to work that are not going to work. So if it comes up at a party, you can say you know what x is, but for your equations, pretend like you don't. Okay? All right, so now, is there an equation that lets us solve for PFY based on this stuff? Well, let me just write one down, the one that's going to work, and we'll check out that it works. So how about this one? 2 times AY times PFY minus PIY is equal to VFY squared minus VIY squared. Okay, so let's check that it works. PFY is in it, so that's good. And now all the other variables that are in it need to be known. AY, we know. PIY, we know. VFY, we know. VIY, we know. So this should work. Okay, what's AY? Yeah, perfect. Negative 9.81. PFY is what we're, yikes. PFY is what we're trying to calculate. PIY is 1.5. And that's equal to VFY 0 squared minus 16.90 squared. So simplify a little. You have negative 19.62 times the quantity PFY minus 1.5 is equal to negative 16.90 squared. Can someone calculate what's 16.90 squared and then divide it by 19.62? 14? Okay. 14.56. And actually, that's not quite there yet. We have PFY minus 1.5 is equal to 14.56. And now add 1.5 to both sides, and we get that PFY is equal to 16.06 meters. Any questions about that? Okay, now we want to figure out how far away the ball lands, how far away horizontally it is where the ball lands. There's no reason to change the coordinate system, anything about the coordinate system. Is there any reason to change either of our two instants? Yes, we have to, that's right. So now we're trying to find something about the instant right before the ball hits the ground. Since that's not either of the two instants we chose before, we have to change one of them, you know? And so we're still gonna keep our time equals 0 the same. But our time final now is going to be the instant right before it hits the ground. And now we can think about the variables we know and what we're trying to solve for. Do we know how long it takes for the ball to hit the ground? No. Acceleration, we know, is 0, negative 9.81. Do we know the position at time equals 0? Yeah, well, actually, since we didn't change anything about time equals 0, all the old sub I values are still the values. So this is 0, 1.5. Do we know anything about P final? We know one thing about it. We have our coordinate system on the ground, our origin on the ground, and when the ball hits the ground, then that means y is going to be equal to 0. Okay, so we don't know anything about PFX. That's what we're looking for. But we do know that PFY is equal to 0. V initial is the same thing it was before. That was 36.25, 16.9, 36.25, 16.90. And then do we know anything about the final velocity? Well, it depends if you're talking to people about physics at a party or trying to use the equations. At a party, you know that the x component is going to be 36.25 at time final. But as far as the equations go, pretend like you don't know anything about that. Just leave that off. Okay? Pretend that you don't know that the x velocity is going to stay the same the whole time, but it is. All right, is there an equation that lets us solve for PF? The answer is no. No equation works. So instead, let's try to solve for time final. Okay, so is there an equation that lets us solve for time final? I think this one does. PFY is equal to PIY plus VIY times time final plus 1/2 AY time final squared. It has TF in it that we're trying to solve for, so that's good. Everything else in the equation is known, so we can fill this out. So it says 0 is equal to 1.5 plus 16.90 TF minus 4.905 TF squared. How do we solve this for TF? Quadratic formula, yep. So this is our A, this is our B, and this is our C. And if you use the quadratic formula, you get TF is one of two things, negative 0.086 or 3.53. No negative times ever in this class, and so we want the positive one. Okay, so now the idea is we've calculated this time, and so this is another thing that we know. And so now we can go back and check if we have enough information to solve for PFX. Well, this equation will work now. We'll check it. But PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. PIX is what we're trying, PFX is what we're trying to find. That's in it, so that's good. We know this, 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 and this. So this equation will work. Okay, so PFX is equal to, what's PIX? 0, yep. What's VIX? 36.25. What's TF? Yep, 3.53. And now the last thing that can mess you up, what's AX? 0, right. It's really easy to make the mistake of writing negative 9.81 there, but it's the X component that we're using now. And so now PFX, just multiply those out, and you get 127.96 meters. 300, about 400, a little over 400 feet, you know. So there you go. Any questions about that problem? Okay, well, that's it for today. I'll give you a couple of assignments like this to work on, and feel free, well, I guess it wouldn't be till Monday, but feel free to ask questions about these if you have trouble with them on Monday. All right, that's all.